Okay, so today we are starting our lecture on electron configuration. In your timeline, this is going to be known as the electron cloud model. Okay, and so electron configurations is the arrangement of electrons around the nucleus of the atom. So previously, with Rutherford's model, we knew there was a nucleus. We knew there was this tiny, dense, positively charged, massive center of the atom, and we just figured that there were electrons all around it. Okay, there's somewhere out there. Then we got to the Bohr model, and because of the spectrum lines, we figured that there were energy levels that these electrons would jump up to and then return and give off a system of light, but that only worked for hydrogen. Okay, and so for higher numbers of electrons, they weren't just jumping up to another energy level. It was a bit more complicated than that. And here we're explaining the complications beyond the Bohr model. All right, so there are 4 rules for electron configuration. Okay, rule 0 is that orbitals, for each orbital, can hold a maximum of 2 electrons. That is rule 0. Okay, so what is an orbital? Okay. An orbital is a region of space Okay, so an orbital is it's not an actual physical thing. It is a region of space. Okay, it is a region Okay, the region of probability space, which means it is given by it is a volume, right? It's a space around the nucleus of the atom where you are going to find an electron that has a particular amount of energy 95% of the time. Okay. And here's how I like to kind of describe it. Imagine you have a darkened room with a light bulb in the middle of it, and the entire room is filled with moths, right? If it's dark, the moths are anywhere throughout the room, yeah? But if you turn on the light bulb, where are the moths going to go? They're going to go to the light. So there would be and they're all going to be attracted to it. And so there would be a region of space that contains 95% of those moths. Yeah? Does that make sense? Okay, so it's not necessarily to contain all of them, but it'll contain 95% of all of them. Okay, that the shape of that space is akin to what an orbital is. Can you guys envision that? Okay, so an orbital is where an electron will be 95% of the time if it has a particular energy state. Yeah? Okay, orbitals have different shapes, and we're going to get into those shapes a little bit later. Okay, but this is our rule number one. Each orbital can hold a maximum of 2 electrons, and an orbital is a region of probability space where you'll find an electron 95% of the time. Okay, rule 0. What's that? Rule 1 is called the aufbau principle. And you have to say it like that. Aufbau. Because we are Stern and we are German, and it's funny. Aufbau. A-U-F-B-A-U. Aufbau principle. Okay, and the definition of this, okay, is that electrons fill the lowest energy before occupying higher ones. Orbitals first. Electrons fill the lowest energy orbitals first before occupying higher ones. Okay. This concept is called ground state. Okay, this is when electrons are at their lowest energy level. Okay, so when all of the electrons are at their lowest energy level, they are occupying what's called the ground state. Okay, when they get excited, when they absorb energy, they're at an excited state. They have more energy than they should. When they return to ground state, that is when they release their photons that have the colors that we saw. Yeah. So excited electrons, they have energy, they're moving around, and then they relax and they return to their ground state. And that's where we get our colors from our emission spectrum. Okay, and this is because atoms are like ogres, which are like onions. They have layers. Yes, I see a couple of smirks. You get the Shrek reference. Okay. Because ogres, they're like onions. We have layers. All right. Okay, they have layers and they fill from the inside out. Okay, so this works well. The aufbau principle works well for small atoms, but as we get larger and larger, there are exceptions to the lower energy level rule, and so that's at the higher end of what we're going to be covering in here. and we'll show you the one exception that we're going to be worried about at a later time. All right, so rule 2. Rule 2 is Hund's rule. Okay, also known as the roommate rule. Okay, and for this, we're going to show our rooms. All right, so Hund's rule. Hund's rule, where are we? Electrons will occupy empty orbitals before empty orbitals. Oops. Empty orbitals in the same sublevel. Not before repeating, before pairing up. Okay. So if you have ever played travel sports or gone on a trip, on an overnight trip for any kind of organization where we have other students. Okay. Okay. And we have our hotel rooms, right? You have a whole bunch of hotel rooms. You are going to, and you're on the same floor. Okay. So let's say you've only got three hotel rooms on your floor. Okay. And there are 4 of you trying to occupy those hotel rooms. Right? What's going to happen is you guys are going to fill one for each room up before you have a roommate. Yeah, which winds up having 2 people together and then 2 solos. Yeah, that makes sense? Okay, so that's the idea, is that because electrons repel each other, okay, they all have negative charges, because they repel each other, they're going to separate to their own orbitals before they start rooming with something that they're repelled by, right? Before they have 2 negative charges in the same room, they're going to separate to the different rooms before we start rooming up. Does that make sense to you guys? Okay, so, all right, so, so we have electrons repel each other. Okay. Okay, because like charges repel. Okay. And single occupancy reduces repulsion. Okay, so electrons aren't ready to leave the atom if they're in their separate orbitals. All right. So, anyways, electrons, as we add electrons to these are our hotel rooms, by the way. As we add electrons to our hotel room, they're going to add to their own they're going to occupy their own room first before they add a second electron. Now you may be asking yourself, what's up with the arrows? Why is one up? Why is one down? This brings us to rule 3. Which is the Pauli exclusion principle. Okay. Okay, the Pauli exclusion principle says that no two electrons can have the same set of quantum numbers. Huh? What is a quantum number? Okay, I'm not expecting you to know this by name of quantum number. Okay, this is the technical version. Okay, I want you guys to think of this as an address. Okay, the set of quantum numbers is undo. Let's select. You don't want to select, do you? Okay. Okay, so think of the set of quantum numbers as the address. Okay, and no two electrons around an atom can have the same address. All right? And so electrons in the same orbital, right? Because we can have how many electrons per orbital? Rule 0, we can have 2 electrons per orbital. So if electrons are in the same orbital, okay, they must have opposite spin. All right, so what the heck does that mean to have opposite spin? All right, which brings us to Faraday's law. Which I do not want you to write down. I want you to watch. I want you to try and conceptualize what we're talking about. You are not going to be tested on Faraday's law, but I want you to understand where this comes from. Okay? Faraday's law says that moving electrical fields or charges create magnetic fields and vice versa. So if you have a moving magnet, it'll create an electric field. If you have a moving electric field, it'll create a magnetic field. Right? They work back and forth. Okay. So, and there's some really cool experiments. I'll show you guys a magnet traveling through a copper tube and how it like floats through the copper tube. It's like dope stuff. Anyways, electrons an electron will spin. Okay, so let's say it's spinning this direction, right? So It'll go into the page on the right and out of the page on the left. Yeah? Okay, so I want you to take your fingers, okay, which means it's spinning like this. Right? That makes sense? Okay, can you guys see the spin? I have the laces on it particularly so you guys can see it, right? So it's spinning like this. Take your fingers of the right hand and curl them in the direction that you see the ball spinning. Right? So it should be like this. Yeah? What direction is your thumb pointing? Up. For all of you, it's pointing up, right? No matter your perspective on this, if the ball spins in this direction, your thumb is pointing up. This is how, in physics, we describe the direction of a spinning object. Okay, it's called the right-hand rule. And in this particular case, this is an up spin. This has up spin. Yeah? Now, if we take the same ball and we spin it the other direction, right, which, okay, so if it's spinning this way, then our fingers curl like that, right? And where's the thumb pointing? Down. So that's the opposite spin. We have one spin going this way. We have one spin going that way. Yeah? Okay, so we have a second electron. Okay, spinning on its axis, where it has that spin, and it is considered down. Okay. So with these electrical charges that are spinning, they are creating a north pole and a south pole magnetic field. Right, so you know a magnet, and you have one end you have north and south poles to a magnet. Right? In other words, you can't, if you hold a magnet one way, they'll attract each other. And if you flip one of them around, they repel each other, right? Okay, so if you have, those are called poles. So if you have a north pole to south pole, they'll attract each other. But if you have a north pole or north pole, they'll repel. Yeah? You guys remember that for magnets? Okay, so if you have two electrons that have the same spin, not only are they going to be electrically repellent, they'll repulse each other because they have the same electric charge, they will also repel each other because they are creating a magnetic field that is in the same direction, and that'll also push themselves apart. Yeah? But if you flip the spin, they're more attracted to each other, or it's part of the magnetic attraction, overcomes the electric repulsion, which allows two electrons now they can tolerate each other in the same orbital. Does that make sense to you guys? Right? So normally they would repel because they have the same electric charge. But because they're moving electric charges and they're spinning in the opposite direction, they can be in the same orbital because they are less repellent to each other. We good? Okay, that's the main idea behind Pauli exclusion principle. Okay, so we have up spin and we have down spin. So let's come back up here. That's why we drew these in two different, with an up and a down, because these electrons are in the same orbital, but the only way they work is if one is up spin and one is down spin. Yeah? Okay, those are the rules that you will follow. Okay, now, as we get more energy, that's not supposed to be there. As we get more energy, energy levels have the first energy level has a sublevel, okay, called S. And that's the only one. And it holds 2 electrons. The second energy level, actually, you know what I need to do is I need to show you guys a periodic table. And our first energy level is okay. Come on, let me have my pen back. There we go. This first energy level going straight across, kind of like yesterday, how we talked about the first circle having 2 electrons. Same thing applies, but this first energy level having 2 electrons has one sublevel, okay, called S, okay, and it has 2 electrons, 1, 2. Okay. The second energy level has 2 sublevels, S, and P is the name of the second sublevel. S has 2 electrons, and it's these 2 guys right here, 3 and 4. And P has 3 different orbitals. All right, so sublevel, and then let's do number of orbitals. Okay, this has 3 orbitals. Okay, S only has 1. P has 3 orbitals in the sublevel. I know it's all kind of jargon here, but each orbital has how many electrons? Can hold how many electrons? 2. If we have 3 orbitals in the P sublevel, and each one holds 2 electrons, how many is that total? That's 6. 1, 2, 3, 4, 5, 6. What? These guys, this is called the P block over here. This over here is called S. All right, so this column, that's the S block. This is the P block. Okay. Now, third energy level. Third energy level has 3 sublevels. It is S, P, and D. There's 1 S orbital in the third energy level. There are 3 P orbitals in the third energy level. And there are, follow the pattern, 1, 3, 5. It's odds, right? 1, 3, 5. Okay, so if there's 5 orbitals in the D sublevel, each one fits 2 electrons. How many total electrons is that? 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my God. Oh my God. It's making sense now. This is why the periodic table is shaped like this. This is the D block here in the middle. Okay. Then finally, the fourth energy level. Actually, it gets higher. Fourth energy level is going to have S, P, D, and F. S is going to have 1, P is going to have 3, D is going to have 5, and F will have 7. Okay, 2 times 7 is 14. These guys right here actually fit in this area. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay, so for oxygen, we're going to fill out our electrons and we're going to create our address. So oxygen is atomic number 8. Therefore, we have 8 electrons. So according to the aufbau principle, we start at the lowest energy level for our first electron. Okay. First electron goes there. Second electron, we have to obey Hund's rule, okay, which means that we have to fill up an orbital before we have, at that energy level or that sublevel, before we can accept a roommate. Well, there's only one sublevel. There's one S sublevel. Okay, so it's ready for the roommate. Pauli exclusion principle says it has to have the opposite spin. So it needs to be down, okay, in order to fill in with its roommate. But that's just 2 electrons. Okay, the next electron, okay, we filled this up so it goes to the next highest energy level, which is the 2s, and we fill it with an up spin. We have filled all the rooms, or we don't have any other sublevels or any rooms in this sublevel, so this next electron must be down. It's got a roommate, opposite spin. All right. The next sublevel and the second energy level is this one up here, these 3 rooms. We still have 4 electrons to put in there. According to Hund's rule, we put 1 into each room before they have roommates. Up, up, and up. By convention, they should all be the same direction. Okay, but we still have 1 more electron to account for, right? This is 8 electrons. We need 1 more electron. Okay, but we have 1 in each room, so now we can have a roommate, according to Hund's rule, roommate rule. We can have a roommate, but the roommate has to be opposite spin from the electron that was there first. So that comes back over here in the first one, and that's down. Okay, this corresponds with up, down, 1s, 2s, up, down. And so now we're ready to write the address of oxygen. Okay? It is 1s, 2 electrons in that sublevel, 2s2, 2p, 1, 2, 3, 4. This is the electron configuration of oxygen. 1s2, 2s2, 2p4. Okay, so check this out. You don't need, however, a diagram to do this. Oh, I don't like that at all. Notice our first energy level. Right there. You guys remember yesterday with the Bohr model, we were drawing our circles? First energy level had how many electrons? We had 2 in that first circle, right? Well, lo and behold, first energy level, 2 electrons. First energy level, 2 electrons. Yeah? Second energy level yesterday had 8. right? The second circle had 8 electrons. Well, this model breaks that up a little bit. We have 2. Let me use a darker color here. We have 2 electrons. These are our 2s2 electrons. Okay, and then to go to oxygen, we have 2p4. 1, 2, 3, 4. There's our 4th electron, right? Okay, notice how many electrons can we fit here in this 2p block? The total we could fit would be how many? 6, right? Look how wide this portion of the periodic table is. Dun, dun, dun. Third energy level. Let's look over here. 3s. Oh, and that would take us to the end, right? 2p. 2p would take us to the end of this energy level, yeah? So we do another electron. We go to, say, 11. We tend it up to 11, right? Nobody gets that joke. Ask your parents. You know the joke? You guys need to watch. This is Spinal Tap. It's really funny. Although it might be R, so I don't know if I can officially recommend it to you guys. Anyways. We go to the 11th electron. That's down here, sodium. This is one we did yesterday. Where we had the single electron out there. Well, that single electron was in the 3rd energy level, and it would go here after we fill these guys up. Okay, then we add a second one. It's going to go here. Well, that brings us to magnesium, which is at the end of this first column. As soon as we add another electron, we're all the way across over here at aluminum. That's going to be the first electron in the 3p. Oh, so wait, this rectangle, that's where we start the p sublevel. This rectangle, including helium, this is the S. Oh. These guys in the middle, these are the D block. D, yes. I wish there was more rhyme or reason to this, but there is not. So I did show you these over here. These that is what the S looks like. That is what the P looks like. That's D. And this is F. Okay, and I'll let you guys do the math, but there's 1, 2, 3, 4, 5, 6, 7 orbitals. Tune in, guys. There's 7 orbitals down here. Each orbital holds 2 electrons. That means there's a total of 14, right? So we come back to our periodic table. These guys right here fill this space. So we start counting here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Oh my God. This is why the periodic table looks the way it does. This is why we have it up in these different blocks of rectangles. It's because of the electron configurations. Similar electron configurations offer similar chemical properties. They're not the same, but they're similar. And so they have patterns. All of the ones in this first... Oh, it's going to erase the whole thing, isn't it? Crap. Okay. All of the ones in this first column right here are going to have similar chemical properties. Second column, similar chemical properties. This last column, these guys don't react with anything. We'll get into that later. These all have similar chemical properties because they all have similar electron configurations. it is now that I can release you to do your assignment that we posted earlier. And we'll finish the lecture here.